Hi everyone. Thank you for coming to my thesis presentation today. My name is Jianyu Fan. My thesis topic is Advances in Soundscape and Music Emotion Recognition. There are two parts in my thesis presentation. The first part is Soundscape Emotion Recognition. I will present several studies and analysis. The second part is Music Emotion Recognition. There are two subsections in the second part. I will end the presentation with my contributions and conclusions. The Soundscape Emotion Recognition. What is soundscape emotion recognition? We define soundscape emotion recognition research investigates computational systems to recognize the perceived emotion of soundscape recordings. There are three keywords here: computational systems, perceived emotion, and soundscape recordings. What is a soundscape recording? This image and recording can help us understand what is a soundscape recording. It is an acoustic environment next to Lake Louise, Banff National Park, perceived and experienced by us. We record this sound using a microphone at a given location at summertime. So people perceive emotion from different soundscape recordings, which will then affect their mood and feelings. Therefore, we want to study the perceived emotion of soundscape recordings. To understand why we focus on perceived emotion, we introduce three types of emotions while listening to music and sound. The first one is intended emotion. Artists decide which intended emotion they want their artwork to convey. And perceived emotion is emotions that are communicated and expressed by the source as perceived by listeners. There is also intended emotion, which are emotional reactions that the source provokes in an audience. It is what the audience feels from the source. For example, angry music makes some people feel happy. We focus on the perceived emotion in our studies because perceived emotion is relatively objective and is less influenced by factors such as mood and listening environment. And we are interested in whether we can build a computational system to predict the perceived emotion of soundscape recordings. We investigate different computational systems to predict the perceived emotion of soundscape recordings. In our case, computational systems are machine learning models. The input of the system is a soundscape recording, and the output is the representation of perceived emotion. Before building soundscape emotion recognition models, we need to answer these research questions. Do people perceive the evocated emotion of soundscape recordings? If so, can we build a machine learning model to predict the perceived emotion of soundscape recordings? How does mixing two soundscape recordings have an impact on the perceived emotion? We conducted several studies to answer these research questions. First, we did a pilot study demonstrate that people can recognize the perceived emotion of soundscape recordings. And the pilot study also demonstrates the feasibility of modeling the perceived emotion of soundscape recordings. Then we built the first publicly available large datasets for perceived emotion of soundscape recordings and experiment the ranking-based emotion annotation methods. Next, we experiment deep learning approaches to improve the performance and obtain the state-of-the-art models. Finally, we model the perceived emotion of the mix and analyze how mixing have impact on the perceived emotion. First, we design an online study. There are two major types of models of emotion in the affective computing field. Categorical models use discrete labels to represent emotions. Here is an example of Ackermann's 6 basic emotions. The other type is dimensional models. which use Cartesian space with continuous dimensions to represent emotions. The most famous one is Russell's circumflex model. We choose dimensional model because it offers a simple interface. It is capable of describing rich emotions. It is convenient to provide transition between emotions due to its continuous nature. We conduct an online study and select 120 soundscape recordings based on Schaeffer's taxonomy, which contains 6 categories. We had 20 participants annotate soundscape recordings on the pleasantness and eventfulness axis. Our interclass correlation coefficients shows that there are high level of agreement in terms of pleasantness and eventfulness of soundscape recordings. This answers the first research question. People can perceive the evocated emotion of soundscape recordings. Berglund suggested that these 2 dimensions, eventfulness and pleasantness, are compatible with Russell's circumflex model of emotion, which contains 2 dimensions, balance and arousal. And balance and arousal are commonly used in the affective computing field. Here we use pleasantness and eventfulness, but in the following studies, we use the term valence and arousal and add explanations of pleasantness and eventfulness for our study participants. Now we need to prove whether it is feasible to model the perceived emotion of soundscape recordings. So we extract 98-dimensional audio feature vector. We use a 2-way stepwise regression model, and input of the model is mean and standard deviation of features of a soundscape recording. The output is the mean value of pleasantness and eventfulness of a soundscape recording obtained from 20 participants. This table shows the result of predicting eventfulness and pleasantness. In general, predicting eventfulness is easier than predicting pleasantness. This is not surprising and consistent with the rest of the literatures on affective computing. Also, we noticed that when not using sound as indicators, the performance improved a lot. The category of sound as indicators influence on the general performance because of the semantic information. Sound as indicators also embedded with cultural and personal information, which is not learned by the model. Here is an example of sound as indicators. We compared our model with a model trained based on a sound designer's data, and a model trained based on each participant's data. And we can see our model performs better than all of their models. Now that we prove it is feasible to model the perceived emotion of soundscape recordings, we can build a large dataset for better models. We built Emo Soundscape dataset. First, we use Freesound database, and we select candidates based on Schaeffer's taxonomy. The recordings are manually selected to ensure quality. Then recordings were automatically segmented by a background and foreground classifier that keeps audio regions with consistent characteristics. We end up having 13 excerpts. Each is 6 seconds. Traditionally, researchers use rating-based annotation methods. However, rating-based annotation methods have high cognitive load and low agreement. We select the ranking-based approach because it is a simple task and there's a high level of agreement. To efficiently collect annotations, we use quicksort algorithm to create pairwise comparisons. For the first iteration of the algorithm, we select one audio sample as the pivot and create pairwise comparisons by comparing the pivot with the rest of the samples in the dataset. Then we collect 3 annotations for each comparison and determine the result to be the one that provided by at least 2 annotators. Now we can split the dataset into 2 subsets. One is lower than the pivot, and the other one is higher than the pivot. We repeatedly select new pivot in each set until each audio clip receives the rank of valence and arousal from 1 to 1213. Here's our online study interface. For each pairs comparison, participants is asked to compare which audio have a higher valence or arousal. We have over 1,000 trusted annotators, and they passed the quiz before participating in the study. Our inter-annotator reliability shows that there's a fair level of agreement. Each trusted annotator took approximately 13 seconds to perform a pairs comparison. This also shows that annotators carefully listen to both audio clips. Next, we experiment deep learning approaches to improve the performance and obtain the state-of-the-art models. After the feature selection, the input of the model are 54-dimensional features. In terms of output of the model, we convert ranking of the valence and arousal from 1 to 1213 to a range of rating values, 1 to -1. So the output of the model will be real value of valence and arousal. We experimented on different architectures, and we used convolutional neural networks and long short-term memory recurrent neural network. We used fine-tuned approach on the VGGH model, which is a CNN model trained for sound event classification. And we use transfer learning approach by using VGGH model for embedding extraction and pass to the support vector regression model. We also use support vector regression as a baseline model. Here's a result of different architectures. When using CNN, we obtain the best result for arousal. And when using fine-tuning approach of VGGH model, we obtain the best performance of predicting valence. Finally, we model the perceived emotion of the mix and analyze how mixing have impact on the perceived emotion. Now we have a model to predict the perceived emotion of a soundscape recording. However, when generating sound design, the sound designer needs to mix different recordings. Therefore, besides knowing the perceived emotion of each recording, it is also important to know the relationship of the perceived emotion of each recording and the perceived emotion of the mix. We use a linear regression model to study this relationship. We find that predicting the perceived emotion of the mix within Schaeffer's category is easier than predicting perceived emotion of the mix between Schaeffer's categories. We believe this is because the texture of soundscape recordings within the same category is more homogeneous. When mixing them together, it introduces less contrast so that the perceived emotion is more predictable. Also, we found that when the difference between arousal of two soundscape recording ratings is larger than a given threshold, it's highly likely that the rating of arousal of the mix lies in between the rating of arousal of two soundscape recordings. This is also true for valence. This corresponds to the findings that the mixed soundscape recordings occurs on a trajectory from one soundscape recording to another one. Here's our demo video of our soundscape emotion recognition model. So why we do soundscape emotion recognition? Currently, sound retrieval systems are based on text description and semantic text. With the soundscape emotion recognition model, we use high-level features such as perceived emotion. For example, in this interface, Users can drag the curve of valence and arousal so that the system will return the most suitable soundscape recordings to match both semantic and emotion annotations. With such a sound retrieval system, we can use it for computer-assisted emotional sound design. In the traditional pipeline of sound design, sound designers need to search in a database and listen to each audio clip, then add the suitable audio to the visual scene. For example, here we have two visual scenes of door open, and we can listen to both door open sound. With a soundscape emotion recognition model, we can add emotion descriptors to simplify this process. We are using the model for several different applications. First, we are integrating our model to Freesound database so that users can label their soundscape recordings with perceived emotion. We have also been using our model in the emotion computer-assisted sound design system. After the user inputs the text description and the emotion value, the system will return suitable sound and generate a sound design that match both semantic and emotional expectation. Then, it has been used in a generative video system, Seasons, a computational system that creates an ongoing video sequences joined by slow visual transitions and enriched with music and soundscape recordings. And we have also used it for MASM, a music agent architecture, which does machine improvisation for live performance. MASM plays experimental music and free improvisation. We have used the soundscape emotion recognition model to study computational musicology. Specifically, we used the soundscape emotion recognition model to analyze Chinese and Western classical music comparatively. We will talk about that later. We have found interesting results in soundscape emotion recognition research, and we have used it for several applications. With my background in music, I was interested in exploring computational approaches in music emotion recognition. I will describe the first part of a music emotion recognition study, ranking-based experimental music emotion recognition. The music expresses emotions. The music emotion recognition is used computational approaches to recognize the emotion of music recordings. There is a growing industry of digital music. All of these platforms have millions of users. They are already emotion-based music retrieval systems. However, they are mainly built for popular music, such as rock, pop, country, and for non-popular music, there are few studies. And there's no such study for experimental music. This project is also under the background of building a computer-assisted system to perform experimental music. So there are two research questions. Do people agree with each other regarding the perceived emotion of experimental music? If so, can we build a machine learning model to predict the perceived emotion of experimental music? So we curate 100 experimental music excerpts and 40 popular music excerpts. The average duration is 6 seconds. We collect annotations of valence and arousal using the same ranking instrument for our previous crowdsourcing study. Our inter-annotator reliability shows that people agree with each other regarding the perceived emotion of experimental music. We designed the smooth binary search of rank support vector machine model. Here's the step of SRSBM. First, we choose odd number of clips as a pivot to compare with the test samples. And we judge whether the test sample is higher or lower than the majority of the pivot and move the test sample. We recursively apply this process until the set of subset is 2. we use smooth binary search for different ranking algorithms. The window size is the number of pivots to select for comparison in each iteration. We compare the smooth rank SVM with several other popular ranking methods. Goldman crystal gamma measures the association between the predict rankings and the ground truth annotations. It ranged from -1 to 1. From the results, we can see the SR-SVM performs best comparing with other models. When the window size is 3, we obtain the best result. We demonstrate it is possible to use machine learning models to predict the perceived emotion of the experimental music. Now we introduce the next subsection of music emotion recognition, a comparative study of Chinese and Western classical music using soundscape models. Typically, model trained based on soundscape recordings does not work for music, because high-level music information such as harmony, melody, and orchestration are not learned by the model. However, when studying classical music, we found both Chinese and Western classical music are referring to the concept of soundscapes. For example, ancient Chinese books talks about sound and nature and music. And for Western classical music, Debussy was inspired by the soundscape in nature for his compositions. And researchers found fractal geometry in bird sounds, Bach, and Mozart's music. Therefore, we intend to test whether soundscape models can analyze Chinese and Western classical music. We address this question through a comparative study of Western and Chinese classical music with music information retrieval and affective computing techniques. Here are 2 examples of Western and Chinese classical music. So our research question is, can we use pre-trained soundscape emotion recognition models and pre-trained sound event detection models for classic music analysis? We curate CCMAT and CCMAT dataset, which are selected based on an online database. There are 400 excerpts in each database. We include diverse instrumentation to cover various timbres. We manually segment each piece and keep each segment between 8 to 20 seconds. And we use the same ranking-based annotation instrument to collect annotations of balance and arousal for both datasets. We explore whether we can use a model trained with diverse soundscape recordings to analyze CCMAT and CCMAT. For sound event detection model, we use the VGGH model as a feature extractor to convert the audio input into latent feature vectors and feed them as input to SVR models for emotion prediction. Regarding SER, we train 2 soundscape emotion recognition models from scratch and use them to extract the embedding vectors from soundscape recordings and pass the embeddings to support vector regression models to train and predict the perceived emotion of CCMAT and CCMAT. With the 10-time shuffle, and each time 10% of the dataset is for testing and 90% is for training, and there's no overlap between train and test set. Here are the results of using SED and SER as feature extractors and combined with support vector regression to predict the perceived emotion of classical music recordings. According to the previous studies, arousal is easier to predict. And for both soundscape and music, arousal is determined by the level of eventfulness and energy. In contrast, valence of soundscape is mainly determined by the timbre, and valence of music is represented by high-level information such as harmony, melody, and orchestration. And sound event detection model does not consider the latter information. However, the VGGH model works significantly better on Chinese classical music. This implies there are certain similarities existing between Chinese classical music and soundscape recordings. the overall performance of using soundscape emotion recognition model is not as good as using the sound event detection model. I think this is because the BGG model was trained on audio set, a large-scale dataset, whereas soundscape emotion recognition model are trained on emo soundscape dataset, which is significantly smaller and less diverse. And the fact that the soundscape emotion recognition and sound event detection model works better on Chinese classical music emotion recognition provide evidence that certain similarities between Chinese classical music and soundscape recordings, which permits the transferability between machine learning models. Our method of analyzing classical music providing novel perspectives to the IMIR community. So we introduce our work of soundscape emotion recognition. First, we define the fundamental psychological questions, and we prove the feasibility of modeling perceived emotion. Then, we describe the first publicly available dataset and provide the state-of-the-art and human competitive model. And we have been using these models for different applications. And there are existing and potential applications of our work. We have used the soundscape emotion recognition model in computer-assisted sound design, interactive music performance, generative video system, and computational musicology. We are building our tools for sound retrieval. In the area of big data, our technology helps people perceive the world and help people's emotion can be better understood and build innovative applications to change the way that people design and analyze artworks. Also, during my doctoral studies, we published 3 journal articles and 17 conference papers. I was the first author of 10 papers. We have also presented 3 artworks in different conference and media festivals. Finally, I will discuss our limitations and future works. Currently, we do not include social demographic factors when collecting annotations. However, previous study shows that social and demographic factors are important for emotion recognition. Also, we should consider contextual information for emotion recognition, such as time, location, and mood of the listeners. We should also investigate the difference between intended, perceived, and induced emotion. Our online annotation instruments can be improved to achieve high agreement, low cognitive load, and high efficiency. We can also try other deep learning architectures. Here are the references. And in the end, I want to thank to my supervisor, committee member, and examiners, Professor Pasquet, Professor Bizuki, Professor Lin, and Professor Tanatakis. I will also thank my founding parties, NSERC and SSHRC Canada. And finally, I want to thank my lovely lab mates in the MagTech Creation Lab. Thank you.